Communities along the freshwater Mississippi River are facing a growing threat.
Gets most of our attention. The middle of the country is suffering as well. Up and down the Mississippi River Basin, below average.
Satellite images released earlier this week have triggered a red alert among geologists after they revealed a dramatic and unexpected rift forming beneath the Mississippi River. The images, gathered from multiple orbital observation platforms over several months, show a progressive deepening and widening of a subterranean fissure that stretches hundreds of miles beneath one of the most iconic rivers in North America. This geological anomaly, unlike anything observed in recent memory in the region, has ignited a storm of concern and speculation within the scientific community. The implications are as vast as they are unsettling. Before we start, hit the like and subscribe buttons for more exclusive news. The Mississippi River has long been a stabilizing force in the geological and economic fabric of the central United States. Spanning from the headwaters in Minnesota to the Gulf of Mexico, the river serves not only as a crucial artery of commerce and transportation, but also as a geological spine running through the heart of the country. Yet this very spine now appears to be under threat from deep within the Earth. The satellite data, corroborated by seismic readings and geophysical modeling, points to an ongoing and accelerating tectonic process that seems to have taken root far beneath the river's path. This rift is not a surface-level crack or erosion feature. It is a deep-seated structural opening in the Earth's crust, possibly linked to the ancient but not inactive New Madrid Seismic Zone. Though dormant for centuries, this fault system is infamous for producing some of the largest earthquakes in the continental United States during the early 1800s. However, the newly revealed rift doesn't follow the exact orientation of the New Madrid Fault. Instead, it appears to run obliquely beneath the river, suggesting that a previously unknown geotectonic force may be at play. Geologists analyzing the satellite imagery noticed that the deformation pattern associated with the rift was atypical. Instead of a clean separation or a narrow fissure, the rift beneath the Mississippi exhibits a kind of subsidence and stretching of the crust that is more reminiscent of rifting seen in continental breakup zones like the East African Rift. This means that the Earth is not merely cracking, it is actively being pulled apart. The terrain on both sides of the river is experiencing measurable, though subtle, lateral displacement, raising immediate questions about the stability of the region's topography and infrastructure. What makes this discovery so alarming is the speed with which the rift seems to be developing. Normally, tectonic shifts of this magnitude take place over millennia, but data from satellites like Landsat 9 and Sentinel-1 show visible progression in just a matter of months. Ground-based GPS sensors have recorded shifts in the surrounding soil of up to several millimeters per week. For tectonic activity, especially in an area not traditionally classified as a major plate boundary, such rapid movement is practically unheard of. The implications of this are profound. First and foremost, the integrity of the Mississippi River itself could be compromised. A rift of this nature could alter the river's path, disrupt sediment flow, and potentially lead to the collapse of its banks in unpredictable ways. River systems are highly sensitive to the gradient of the underlying terrain. Should the land beneath the riverbed begin to sink or split further, entire segments of the river could redirect, stall, or even dry out temporarily before new paths are carved. Such an event would have devastating ecological consequences, not to mention the economic impact on agriculture, shipping, and water supply for millions of people. Moreover, the towns and cities lining the Mississippi River are deeply interwoven with its natural course. Major urban centers like St. Louis, Memphis, and Baton Rouge depend heavily on the river for transportation, trade, and drinking water. A shifting foundation beneath the river could wreak havoc on infrastructure. Pipelines, bridges, levees, and dams that were never designed to endure large-scale ground deformation. The satellite images already show stress fractures appearing near critical structural supports along the riverbanks, prompting urgent engineering assessments. Beneath the surface, the geological changes could also influence regional hydrogeology. The Mississippi River interacts with a complex network of aquifers that supply groundwater to surrounding states. A rift might disrupt these aquifers, leading to contamination, loss of pressure, or even sudden subsidence in areas far removed from the river itself. Water tables could shift unpredictably, affecting everything from crop irrigation to municipal water systems. In some areas, wells have already begun to show unexpected drops in water pressure, a possible early symptom of subterranean shifts. Seismic risk is another major concern. While the rift itself may not be a traditional fault line, the opening of the crust in such a dynamic fashion could easily act as a catalyst for seismic activity in nearby fault systems. In fact, since the discovery of the rift, there has been a noticeable uptick in microseismic events throughout the region. Small earthquakes barely perceptible at the surface, but clear indicators of stress redistribution underground. These tremors may precede larger, more destructive quakes, particularly if the rift intersects or transfers energy to the New Madrid Seismic Zone. The last time the New Madrid Fault unleashed its fury in the early 19th century, the effects were so powerful that the Mississippi River itself briefly flowed backward. Entire towns were destroyed, and tremors were felt as far away as the East Coast. The possibility that this newly forming rift could energize the same fault system is not just speculative. It is a growing concern among experts who have long warned that the central U.S. is overdue for a major seismic event. Compounding the urgency is the rift's potential impact on energy infrastructure. The region surrounding the Mississippi hosts a dense web of oil and natural gas pipelines, refineries, and storage facilities. Many of these installations are located underground or along the river's edge, making them particularly vulnerable to ground movement. A rupture in any of these pipelines could lead to environmental disasters of significant scale: oil spills, gas leaks, even explosions. Furthermore, railroads and highways that follow the river corridor could be severed by ground shifts, cutting off supply chains at a national level. There is also a growing concern about the influence of this geological activity on regional climate patterns. While not immediate, a significant shift in the Mississippi River's course could alter local weather conditions by disrupting evaporation patterns, changing heat distribution, and affecting the migratory routes of moisture-laden air masses. Such a transformation in one of the continent's primary hydrological systems could ripple outward in ways that scientists are only beginning to model. The discovery of the rift has triggered a wave of interagency coordination. Geologists, seismologists, hydrologists, and structural engineers are now collaborating in an unprecedented data-sharing initiative. Mobile seismic units have been dispatched throughout the Mississippi Basin, and airborne LiDAR is being used to map even the most subtle terrain changes. Preliminary models suggest that the rift could extend deeper than initially thought, possibly reaching into the upper mantle, which would dramatically escalate its potential for long-term transformation of the region. Another concerning development is the potential for this rift to become a new tectonic boundary over time. While North America is currently considered a stable plate, there have been historical indications of rifting and crustal weakness in the interior of the continent. The Mississippi Embayment, a geologically depressed area through which the river flows, has long been suspected to harbor deep structural weaknesses dating back hundreds of millions of years. The newly discovered rift may be reactivating some of these ancient faults, breathing life into what was once considered extinct geology. While this rift is still in the early stages of formation, the sheer scale and speed at which it's evolving have transformed it into a top-tier geological emergency. Satellite data shows the ground on either side of the river moving apart by measurable increments each week. The middle crust appears to be thinning, which can cause a cascade of other geophysical effects, including increased heat flow from the Earth's interior, softening of deep rock layers, and ultimately the triggering of magmatic activity if the rifting continues unchecked. The energy dynamics involved in such a rifting event are massive. Unlike the more common strike-slip or subduction zones found along coastal regions, continental rifting involves the gradual tearing of Earth's crust from internal pressure. This pressure is usually related to mantle upwelling, the slow but relentless rise of hotter, less dense material from deep within the Earth. If mantle material begins to breach the crust near the Mississippi River, it could lead to volcanic activity, a startling idea for a region with no current volcanic features. But geologically, rift zones can give birth to new volcanic fields, and although that process can take thousands of years, early warning signs could appear within decades. Adding to the complexity is the potential for methane hydrate destabilization. Beneath many of Earth's sedimentary basins lie vast reserves of frozen methane trapped within high-pressure environments. Should the rift cause enough warming or pressure loss in the deeper sediment layers, These hydrates could dissociate, releasing large volumes of methane gas into the atmosphere. Methane is a potent greenhouse gas, and its sudden release could exacerbate climate issues already facing the planet. While this is currently a hypothetical concern, it remains within the realm of possibility given the tectonic activity now unfolding. The role of human activity is also under scrutiny. While natural tectonic forces are undoubtedly at work, some experts are investigating whether decades of deep drilling, mining, and fracking in the broader region may have contributed to the destabilization of deeper geological structures. The Mississippi River Basin has been heavily exploited for oil, gas, and other resources, and the cumulative effect of extracting billions of gallons of fluid from the earth could have triggered or accelerated the rifting process by reducing pressure and altering stress regimes deep underground. Geologists are now conducting comprehensive geochemical analyses of soil and rock samples from along the rift's projected path. These studies aim to determine whether the crust is undergoing chemical metamorphosis that typically precedes the birth of new geological structures. Early signs show mineral changes consistent with increased geothermal activity, a possible indication that the Earth's mantle is indeed becoming more influential in the region's evolution. The situation developing beneath the Mississippi River is not just a matter of tectonic movement. It marks a shift in how geologists and planetary scientists perceive continental interiors. Traditionally, the central regions of large continental plates, far from plate boundaries, have been considered geologically stable. This perception underpins everything from urban planning to resource extraction. The emergence of a rift zone in this stable zone challenges long-standing assumptions about the relative dormancy of Earth's interior beneath the American Midwest. The rift's discovery forces a re-examination of tectonic models, particularly regarding intracontinental deformation. These events are rare but not without precedent. Millions of years ago, similar rifts formed the basins that now hold the Great Lakes. Even earlier, the failed mid-continent rift carved a massive arc beneath what is now Lake Superior. Though it never developed into a full-fledged ocean-forming rift, it left behind vast igneous provinces and clues to Earth's early continental dynamics. The Mississippi River Rift may be another such event in its infancy, but its current pace and complexity suggest it could evolve in unexpected ways. This rift isn't occurring in isolation. Rather, it is forming within a mosaic of older, deeply buried structures, ancient faults, metamorphic belts, and lithospheric weaknesses that are only now reawakening. These inherited structures can localize strain and influence the path and intensity of new deformation. When satellite data was compared to historical geological maps, certain alignment patterns emerged. The rift is threading its way through zones of prior weakness, perhaps guided by scars in the crust that date back over 1 billion years. These inherited paths of least resistance can channel energy and deformation more efficiently than previously realized. Remote sensing data has revealed gravitational anomalies that further complicate the picture. Gravity surveys conducted via satellite suggest a localized reduction in crustal density beneath the Mississippi River. This could indicate the presence of rising mantle material or the thinning of the continental crust. Either scenario suggests that the rift is not a superficial event, but a deep structural transformation reaching toward the planet's mantle. Changes in gravitational gradients have also been matched with shifts in magnetic field intensity over the area, another sign that the Earth's deeper layers are in flux. There is also the biological impact to consider. While often overshadowed by geological and infrastructural risks, ecosystems are among the first indicators of subtle environmental shifts. Riverbanks have shown signs of abnormal erosion patterns, with vegetation receding in some places and flourishing in others. Aquatic species sensitive to temperature and pH have begun migrating differently or failing to spawn. The sediment load carried by the river has changed in texture and composition, indicating alterations in upstream erosion linked to micro-movements in the terrain. Freshwater mussels, a keystone species in many riverine ecosystems, have started to decline in areas previously known for high populations. These early ecological disturbances could foreshadow broader biological consequences if the rift continues to evolve. Atmospheric scientists have also taken note of peculiar changes in radon emissions, a natural radioactive gas that seeps from deep underground. Radon levels near the Mississippi Basin have increased beyond seasonal expectations, often a precursor to ground shifting. Though not inherently dangerous in the short term, these spikes further support the theory that the Earth's crust is actively stretching and opening in previously dormant zones. This data, combined with increases in low-frequency electromagnetic waves recorded in the area, builds a more complete picture of an intensifying subterranean process. The Mississippi River, though ancient, is not a static feature. It is a living system, constantly adjusting to changes in elevation, sediment, and climate. But with a rift undermining its very foundation, the entire hydrodynamic behavior of the river may be set for transformation. Should the rift deepen further, subsidence could lead to ponding, redirected tributaries, or even the formation of new inland lakes. Wetlands could be inundated or drained, displacing countless species and transforming carbon sink dynamics across the basin. The river may eventually split, forming separate channels as the land beneath it descends unevenly. From a societal standpoint, the uncertainty of what lies beneath poses a monumental challenge for policymakers, emergency planners, and infrastructure managers. Building codes across the Midwest were never designed with large-scale tectonic movement in mind. Bridges spanning the river, some of which date back over a century, may not withstand prolonged crustal strain. The risk is not necessarily from a single cataclysmic event, but from the compounding effects of gradual instability, small movements, subsurface shifts, and foundational undermining that degrade structural integrity over time. Insurance companies have begun reassessing risk models, particularly for properties near the river, or dependent on its commercial utility. Already, murmurs of reclassified flood zones and geohazard premiums are being heard in the insurance sector. Without a clear precedent for this kind of tectonic feature emerging so quickly in a populated inland region, financial institutions face immense uncertainty. The agriculture industry, too, is on edge. The Mississippi's fertile floodplain supports a vast percentage of America's corn, soybean, and rice crops. Even small shifts in the river's flow could interrupt irrigation patterns, disrupt planting schedules, or cause saltwater intrusion from altered delta dynamics. There is growing pressure on the federal government to establish a task force dedicated solely to monitoring and modeling the Mississippi Rift. This would likely include not only geological institutions like the USGS, but also the Army Corps of Engineers, FEMA, NOAA, and representatives from major universities. The scale of coordination required echoes responses to major natural disasters, despite the absence, so far, of a single dramatic event. The potential for compound disasters, earthquakes triggering levee failures or tectonic shifts destabilizing dams, has prompted discussions about long-term infrastructure hardening across multiple states. One of the most pressing unanswered questions involves the rift's ultimate trajectory. If it continues to grow, will it form a new basin? Could it eventually split the continent's crust and set the stage for the formation of a new ocean? Though such outcomes are speculative and far off, Earth's geological history is full of similar events. The Atlantic Ocean, after all, began as a rift. If current patterns persist, this fissure could one day delineate the edge of a new continental block, albeit over tens of millions of years. Complicating predictive models is the relative novelty of rift formation in such a heavily monitored era. Never before have geologists had access to real-time satellite data, ground-based sensors, drones, and machine learning tools to monitor the birth of a tectonic feature. While this affords unprecedented observational power, it also reveals just how much is still unknown. Algorithms fed decades of geological data are producing varied and sometimes contradictory forecasts. Some suggest that the rift will slow and stabilize, a failed rift like others seen in North America. Others warn of accelerating crustal deformation driven by deep mantle anomalies that have only recently begun to manifest. This inconsistency in forecasting complicates public messaging. Authorities walk a fine line between transparency and inciting panic. There is a need to prepare without alarming, to educate without overstating the risk. Scientists must now explain to the public what it means for a rift to grow, how it differs from an earthquake fault, why it matters even if there's no immediate destruction, and how to live with the uncertainty of a changing planet. Schools and universities across the affected states are integrating geoscience modules into curricula with renewed urgency. Students are learning not only about the mechanics of tectonics, but about their community's newfound vulnerability. In towns like Cairo, Illinois, and Greenville, Mississippi, local governments are holding town halls to address citizen concerns and discuss contingency plans. These meetings range from pragmatic, how to reinforce levees, to philosophical, how to mentally and culturally adapt to living above an active rift. Beyond Earth, the Mississippi Rift is drawing the attention of planetary geologists, scientists who study rifting and tectonics on other planets. Mars, for example, has massive rift zones like Valles Marineris, which are believed to have formed through similar extensional processes. By observing the Mississippi Rift, researchers can refine their understanding of extraterrestrial geology, using Earth as a living laboratory to interpret features seen through telescopes and rovers on other worlds. If you liked this video, please give it a like and subscribe to our channel. Also, could you leave your comments below and tell us, what are your thoughts on the rift beneath the Mississippi River? Will it get worse? We want to hear from you. Thank you for watching, and see you next time.